and I'm not going to go back to the PowerPoints. What I want to do today is just kind of lecture off the top of my head that there, which sometimes will get me in trouble. As I said, I want to finish today by a little before 1 o'clock, or a little after 1 o'clock at the latest, so that anybody who wants to go to down Dakota, to Stoppock for Dr. Fadi's prayers can do so. That there, unfortunately, we have FYP2 this afternoon, and I can't go. My plan, and I actually was sending emails to Dr. Lillick trying to reschedule it, and evidently there's a whole big meeting going on right now with the industry folks that are coming for that. So there's too many people involved to try to reschedule it. So I won't be going. But I'm going to just, and I will post today's lecture because it will pertain directly to the final project that I will be posting probably over the weekend. And we'll talk about that next week. And that'll pretty much wrap up this course. There's a lot. I do have a couple of things that I need to talk about as far as plotting in a little bit more detail. I did introduce how to do plotting with out of the first chapter with MATLAB. That's there. So, but what I want to talk about today is, let me find one note here. Where's my one note? As I said, I switched computers, and this one's got everything under the sun still installed in it. Word, PowerPoint, there's one note. It should be right toward the top. I use it a lot. Got there. Okay. What I want to talk about briefly is I want to do a little bit of a review on, Thevenin's voltage law with AC circuits. That there. And whenever you deal with and I'm going to start off without drawing the circuit, I'm just going to simply show we've got a branch here with Z1. I'm going to show a couple branches here with Z2, Z3, Z4. I'm going to show here a V1, show a Z5, V2, and a Z6, and a V3. Now, this might be slightly different than the way that you learned it. This is the way that I learned it and the way that I've been teaching that there. But we've got three loops here that we can draw. Now, the way that I normally tell people to do Thevenin's voltage equations is that I always draw the loops clockwise and inside that there. You can draw the loops in any direction you want. You can draw them inside and out. That there. You can, basically as long as all branches are included in a loop and all impedances are included in all voltage sources. But if I draw this all clockwise, I1, I2, and I3, right there. I'm drawing three loops, all clockwise and all internal right there. And I start at the bottom left-hand corner and go across the bottom, and then I go to the right, that there. And, I just have an orderly way of doing it because things kind of turn out nicely if you do this, that there. No guarantee. So I've got 6 impedances, and I can write the equations, and I'm going to go through and write one or two of the equations, and then kind of point out that I don't necessarily write the equations. But first off, you have to show a voltage for each of the three, or polarity for each of the voltages, because those make a difference. Because as you write the equations, you use the polarity that you enter. So if I start off, and I'm going to write for loop 1. So I'm going to say minus V1 right there, plus I1 times Z4 plus I1 minus I3 times, that's what, Z2 right there, plus I1 minus I2 times Z5 plus V2 equals 0. So Thevenin's voltage law says that we start at one point and we go around the loop and we write all of our voltage equations, you know, writing the voltage drops across every voltage source or impedance that there, and we end up back at the same point, and that's going to be equal to 0. Now in this particular case it does equal the voltage at the starting point is 0, because that's why I defined as ground that there. And you know, Kirchhoff's voltage law is the same thing as if you're running a marathon, and I don't know if anybody in this room has ever run a marathon or looked at running a marathon that there, but if you run a marathon and you start at point A and you end at point A, all the uphills equals all the downhills. So if you're 500 meters elevation, you're going to end up at 500 meters elevation. You know, I've ran a couple of marathons that there. You know, I ran my first marathon one day, and then later on, about 6 months later, I ran my second marathon called my last marathon. So I've ran my first marathon and my last marathon and none in between. Marathons are too hard on the body. And I was younger and thinner then, and one of these days, not now since I'm going to retire, I used to, I had a picture of me back in my running days. I used to, that they had it on the wall in the department to prove that I wasn't always fat and out of shape. That there, but regardless, when the old joke used to be in the States, old people would always say that, I had to walk 5 miles to school uphill both ways. Well, it can't be uphill both ways. That there, and I grew up in Minnesota, and I did walk to school. That there, but it wasn't uphill both ways. It was uphill part of the way going to school, and it's uphill part of the way coming home. But that's that there. So we could rewrite this equation, and we could say that it as the form I1, and I've got Z4 plus Z2 plus Z5 minus I2, and I2 is Z5 minus I3 right there, Z2 equals V1 minus V2 right there. Now these two, when you're solving matrix equations, are usually known. What's not known is I1, I2, and I3. So when we go back and we look at this, and if we were to write the other three equations, and I'm not going to spend any time writing the other two equations, but it's going to be of the same form. It's going to be I1 times something plus I2 times something plus I3 times something right there. And of course this is going to be some impedance there. This will be another impedance. And these could be plus or minus right there, and equal to some V. And I'm going to call this Vx, and this could be a V something Y minus VZ, or it could be 0. Because if I look at the first loop, Bri3, the one on the top, there are no voltages for that there. So what we end up with is 3 equations right there. So we've got the form A11, I1, A12, I2 plus A13, I3 equals, no, I3 equals V1. And now this is a different V1 than it's an equation. I21, I1 plus A22, I2 plus A23, I3 equals V2, A31, I1 plus A32, I2 plus A33, I3 equals V3. You know, so you end up with 3 equations, 3 unknowns, right? And this goes back to the last thing we talked about with MATLAB. We have 3 equations, 3 unknowns right there. So we can rewrite this equation as the matrix A, and I'm just going to say A times the vector I equals the vector V, right? That there. You know, we can write it as a matrix in matrix form, because when I take and I multiply, and I'm just going to do the first row, A11, A12, A13 times I1, I2, I3, and I want to say that's equal to V1. If I draw this, that's actually A11 times I1 plus A12 times I2 plus A23 I3 equals V1. That's the way we multiply matrices. And I'm making the assumption that you've done that at one point in one of your math courses. If not, that's the way you multiply. This row times that column will give me this value right here. Now, if I have 2 columns out there, then I would multiply. But for linear circuits, that out there, we only deal with loop equations in this form. So that there. So we could turn right around and we could say that the A matrix times the I matrix equals the V matrix. And we can turn right around and say that A minus 1 times A times I equals A minus 1 times V. Well, these two break off to the identity matrix, which is different than the I matrix. That, I'm going to put a little M there for matrix right there. But that simply means those two multiply out to 1, 0, 0, 0, 1, 0, 0, 0, 1, which is the identity matrix. And that can be dropped. So this is how we would solve any kind of loop equation right there. So now going back to my circuit, and I'm going to grab that. Oh. Oh, what's going on here? Collect that. All right. Boom. Let's just do Control C. And come down here and we'll just All right, there's my circuit right there. And what I want to do is I want to just go through it and write the matrix directly from the circuit right there. So my circuit, my matrix looks like this right here, and I'm going to call this the Z matrix, or the Z matrix right there, and that's the matrix made up of all that there. So this is all the impedance in loop 1. This is all the impedance in loop shared between loop 1 and 2, and this is all the impedance shared between 1 and 3. This is all the impedance shared between 1 and 2. And actually I could write 2 and 1 right there and put a plus right there. This is all the impedance in loop 2 right there. This is all the impedance shared between 2 and 3. This is all the impedance shared between 3 and 1. This is all the impedance shared between 3 and 2. And this is all the impedance in loop 3. So I can do that straight from by looking at the circuit and fill this in. Now, as it turns out, if you draw all your loops clockwise and they're all internal, everything on the main diagonal here has to be positive. Everything off the main diagonal right here is going to be either negative or 0 right there. In 99, you might find a weird case, but 99% of the time that they're, and also this is going to be a symmetrical matrix that there, because you can't have an impedance that's shared between loop 1 and 2 and an impedance that's shared between loop 2 and 1 that's not the same right there. So when I look at this circuit right here, and I'm going to just draw V again, redraw it right here. In loop 1, I've got 3 impedances, right? Loop 1 right here, I've got Z4, Z2, and Z5, right? So I can just write Z4 plus Z2 plus Z5. And I'm sorry, I'm using the Z instead of the Z, but you know what I'm saying right there. And I know my handwriting is impossible at this small. Between loop 1 and loop 2, I've got 1 impedance in Z5. And that's going to be minus Z5 here. And since it's symmetrical, I'm going to put minus Z5 here. Right there. Save myself a little time right there, since we know that this matrix is symmetrical. Between loop 1 and 3, I've got 1 impedance, Z2, right there. This is the only impedance that I3 and I1 both pass through. So I would write minus Z2. And write minus Z2 right there. In loop 3 or 2, I've got 3 impedances. 5, 3, and 6, right? So I would just simply write Z5 plus Z3 plus Z6. Between loops 2 and 3, I've got 1 impedance, Z3, right? This is the only one shared between those 2 loops. So I would write minus Z3, and again, minus Z3, right there. And then in loop 3, I've got Z1 plus Z2 plus Z3, right there. So there's my Z matrix. I didn't write the equations, I just wrote the matrix straight from the circuit. Now I could go through, once I do the V matrix, and I'll do the V matrix in a second here, and I'll do that the same way, right there. I will do that by inspection by looking at the circuit and just writing down all the voltage drops in the circuit. Only I will reverse the sign. In other words, I will use the voltage gains in the circuit. And that goes back to, remember, when I wrote this equation, that I brought V1 and V2 to the other side of the equation, right? So this is minus V1, so it became plus V1 when I brought it over there, and this is plus V2, and it became minus V2 there. And I know I'm talking a little bit quick here, but I want to kind of get through this theory that there. So when I come back and I look at my circuit right here, and let me just do it over here. And where's my circuit? Okay. I just keep putting the same circuit over again. So I'm going to write my V vector right there. And I'm just going to go around loop 1, and I'm going to see that I come out V1 and I go in, I come out the positive of V1 and I come out the negative of V2. So this becomes V1 minus V2 right there. When I go around loop 2, I come out the positive of V2 and out the negative there. So this becomes V2 minus V3 right there. And as I go around loop 3, there are no voltage sources. So now I've got my V vector and my Z vector right there. Now I don't have any numbers in these. I'm just going through them with theory. We'll put the numbers in most likely on Tuesday right there. We'll go through and do this with numbers, and then we'll do it with, and I'll first do it with numbers where I'm just going to say Z1 is equal to 35 minus J20, and that there. So but you got to remember that these Z's, these impedances, are complex numbers right there. And we can easily put these complex numbers in the MATLAB and have it spit out answers for us. Right there. And I'm sure that you took AC circuits theory and you went through this, and solving these equations was a pain in the butt, to be honest, right? Now what I'm trying to do is you look at the circuit, you put in the values, and you put the equations in MATLAB, and out comes the answers in about 3 minutes right there. So we take something that probably took you 45 minutes on your final exam in AC circuits, or 30 minutes on final exam in AC circuits, right? And we're going to learn how to do it in like 5 minutes. That there. Matter of fact, this little trick right here probably would have saved you a lot of time in AC. And I'm not sure, do they teach how to go straight to the matrices in your circuits course, or do you go through and write the equations? You went through and work. In other words, when you saw a circuit like this, you had to write the equations. So you didn't go straight from the circuit to a matrix. Not there. So it does save a lot of time when you can do it that way. But again, the whole idea is you learn the basis. I can go through and I can show that if I wrote the equations, if I multiply these two matrices out, I would get the equations back. So I can go from the matrices back to the equations. And what I'm trying to show here is, let's skip the equations and go straight to the matrices, because the matrices is what we want for MATLAB. Our ultimate goal is to stick this in the MATLAB, and MATLAB requires that we put in the that there. So, once you do this, and the way that I normally would say doing this in MATLAB is that I would say, go through and say Z1 is equal to something. Z2 is equal to something. Z3 is equal to something. I'm just going to put it over here just to save room. Z4 is equal to something. Z5 is equal to something. And Z6 is equal to something. And this could be something like 35 minus J20 plus J10, for example. If those are the three impedances in that, the three elements in that loop right there. So you would put those in, and then you would just simply say that Z, and this is capital Z, is equal to matrix, and what did I have there? Z4, 5, and I can't read my writing because they're so 4, 2, and 5. And come on. All right. This thing is Z2 plus Z4 plus Z5 space, going back to my matrix right there, minus Z5 minus Z5, make sure there's a space there, and then this was minus Z2. Minus Z2, semicolon, and I'm just going to show it on the other line, minus Z5, right there. And this is 3, 5, and 6, right? And space Z3 plus Z5 plus Z6, and this is 3 minus Z3 semicolon. Now again, this is all on one line, that there, and then this would be then, okay, this looks like it's minus Z2 space minus Z5 space Z1 plus Z2 plus Z3, close bracket, and you may not want to put the semicolon at the end because you may want to see what the matrix looks like right there. But you would put that in the MATLAB right there. So the only place that you actually had numbers was before you wrote that matrix where you said what each one of the 6 impedances were. And I gave the example where Z6 had, a 35 ohm resistor, a minus J, 20, that's a capacitor, and a plus J10, that's an inductor, right there. And remember that X of C is equal to minus J1 over omega C, and X of L is equal to J omega L, right? And omega, if you forgot, is 2 pi F, right there. So that's where those numbers come from, and this is kind of a review going back, and we'll come back on Tuesday and work this with real numbers. That there, first off, I'll give impedances, then I'm going to put capacitors and inductors and specify a frequency. Now you can only solve this with one frequency right there. Now you could do this in a way where at the top, and I'll talk about this later, where you said F is equal to 50, and then you said W is equal to 2 times pi times F right there. And then you can say ZX is equal to 30 plus I omega 10e negative 6, for example, or negative 3, where that's a 10 millihenry inductor, for example, right there. Well, we'll go through that there. I don't want to go through this right now, but you could do that there. And then you could turn right around and say that V is equal to, and that was V1 minus V2 semicolon V2 minus V3 semicolon 0 right there. And there's your V vector. And then you can say then I is equal to Z to raised to the negative 1 right there times V, and that will pop out I is equal to and give you some vector with V with I1, I2, and I3 in that there, and you're done. So you can see the process that we're going through to solve a 3x3. Now, a 4x4 or a 5x5 is done exactly the same way with MATLAB. When you took your circuits course, I'm sure you did not see any 5x5s, right? That there, and on a final exam you could not, because you didn't have, they didn't teach the math skills to solve a 5x5 matrix. You can do it using a method called Gauss elimination. There's a way of doing it where you can solve it, where you can go through and manipulate the matrices and solve it. That's usually a more advanced linear algebra subject and I would be surprised, and I don't know what's taught in your linear algebra course, if Gauss elimination was part of that there. Did that term mean anything, Gauss elimination? Probably not. I'm not seeing anybody say, yeah, I remember that. And yeah, I could do that, right? That there. But you can do this easily, right there. And you got to remember, and I'm going to wrap it up here, is that if you're working in industry and you're electrical engineers, you're not microelectronic engineers, you're not circuit engineers. I rarely came across loop equations in my work. I will be honest, I did not do a lot of loop equations because I wrote a lot more software and I did a lot more digital design and I did a lot more with VHDL in terms of doing circuit design using high-level hardware description languages. I wrote a lot of embedded software. I spent a lot of time going through data sheets of figuring out how to hook up, serial I/O chips to microprocessors, and and how to connect, Ethernet, chips up to a microprocessor and how to cable that to another computer. So we didn't do a lot of, I didn't do a lot of circuit analysis. But when you're doing wiring, from city to city using high tension voltage wires with transformers in there, you're going to be writing some matrix equations. So you're more likely to see this than I actually did in my 30-some year career. And I say 30-some year career because most of the time when I was working for industry, I was also, or for the academia, I was also working for industry part-time. So I was doing a lot of work there, but almost none of my work had a lot of matrix equations there. But you'll see that now. So I'm going to stop here at this point. As I said, I wanted to stop before 1. I can't give you exact directions to the Sorrel, those who want to go, but if you go out of campus and then you turn right on there at the light then the next light is John Gombach, and you just follow that around till you see Edelman Plaza. There's a McDonald's and a KFC there. If you turn left there, you'll go till that road dead ends, and you kind of wrap around, and the Sorrel is right in that, near that area. And because the building he lived in was right around that there, because I've been to his house a couple of times. Matter of fact, had to go jump his car once or twice when his battery went dead. That there, so I've been to, so that there, and the Sorrel is right near the house. I haven't been to the Sorrel that there. He used to be the imam that gave the Tawi prayers to the mosque I do go to. That there, so he gave Tawi prayers, but he was the second imam at the mosque where the prayers are being held. At there, so they know him very well. I would recommend if you're going to go, it's going to be crazy because I suspect that there's a lot of people. And the reason I'm recommending, you probably know him as well as any of the other students in UniKL because you're the only students that ever had him in class. That there. I wish I could go, but unfortunately that there. So I will see everybody on Tuesday. That was 35 minutes.
Sir, where should we submit our assignment?
Your assignment, you can submit that next week. Just do it. Is there a due date on what? Today? I'll give you till next week to do that. I'll change the due date. If I don't, hold on to it and remind me on Tuesday, and I'll change it that there.